week, and it's time for our ESERO Ireland Space Careers Roadshow, kindly hosted by Blackrock Castle Observatory. I'm Niamh Shaw, and I'm your host this morning. We have a fantastic lineup of speakers. The theme of our Engineers Week Space Careers program is all things James Webb Space Telescope, upon which to talk about, but really we're talking about careers and about what it is that makes us decide the choices that we do in our careers. And I'm going to just stop talking now and pass you over to our ESERO Ireland manager who runs this program, Stephanie O'Neill. Good morning, Stephanie. How are you?
Hi, Niamh. How are you?
I'm good. I'm good.
What part of the world are you in, Niamh?
I'm in California. It's 10 to 2 in the morning.
Oh,
but
so
there you go.
You're up very late at night, or
yes,
early in the morning.
Well, that's my commitment to Engineers Week. Do you know what I mean? And space. So there you go. There's no clocks in space. There's no clocks in space, Stephanie. So over to you, and I'll come back to you in a few minutes, folks.
Okay. So thank you, Niamh. I've just shared my screen. Can you just tell me you can see it? Yeah.
Yeah, I can see that. No problem.
Brilliant. So listen, good morning, everybody, and welcome to our Space Careers Roadshow. This is a special edition for Engineers Week. As you all know, this is Engineers Week. And we have these roadshows where we bring scientists and engineers in the space sector to share their STEM education and career experience with you. So this is really a chance for you, senior cycle students and your teachers, to see some of the opportunities that are maybe out there and maybe of interest to you. From the start, I want to thank my colleagues in Blackrock Castle Observatory, who work very closely with ESERO, and they manage the Space Careers Roadshows. As I mentioned, there's a series of them. So this is for Engineers Week. We'll have another one for Space Week in October, and we'll have our final one of the year for Science Week in November. And Rob and Danielle in BCO are working very hard today to make sure that this is a really high quality experience for you. So just to look through the format of the day, we've changed the format from previous roadshows. Feedback has told us that maybe they were a little bit long, so we've cut a number of speakers down from 3 to 2, and I'll talk about speakers in a minute. We're on YouTube from the beginning until after our second speaker. And at that stage, we'll end the YouTube stream, and students will have a chance to go into the breakout rooms with John and Giovanna. And that gives you a really good opportunity to have a chat with them. You're up close and personal with these two scientists engineers. So make sure to have your questions ready from their presentations, or any questions that you might have from looking at their profiles, etc., in advance of today. This is a really good opportunity for you to ask the questions, the burning questions that you have. Then after that, we'll have a best question from each of the speaker rooms, and there'll be prizes for the two best questions. Okay. So I want to sincerely thank our speakers for giving their time today. Niamh Shaw is a great friend of ESERO. Niamh, of course, is a science communicator and a space expert at this stage, and she has done a lot of work with us over the years. There's a profile of Niamh on our profiles page if you'd like to learn more about her. So Niamh will be emceeing the event for us today. Dr. Johnny Ward is a space product manager at Irish startup company Ray Astronomy Space System Engineering. And Johnny was involved with scientists and engineers at Ray Astronomy in designing and manufacturing the video system that was on the Ariane 5 launch vehicle for the James Webb Space Telescope. Of course, I should have told you at the outset that the theme for today is the James Webb Space Telescope, and that's a new telescope that was launched on Christmas Day, in fact, and that is due to take over from the famous Hubble telescope. And that leads me into Dr. Giovanna Giardino, and she's an instrument scientist at the European Space Agency. And since 2010, she's been working on the near-spec instrument. Giovanna will be working with the data coming from the new telescope, and hopefully she'll tell us a little bit about that as well. And we're really thrilled to have these exceptional people with us today to share their experience. And their varied experience. I think you'll learn from their presentations. and varied backgrounds. I need to tell you a little bit about Azero. It's a network of ESA offices, or ESA education offices across Europe. There's 20 at the moment, and it's growing rapidly. Azero is the European Space Education Resource Office. So that's really like an ESA education office in each country. In Ireland, it's a contract between the European Space Agency Education Office and Science Foundation Ireland, and that's what I work. And I work on the Education and Public Engagement Department of Science Foundation Ireland. So what we do is try to promote science, technology, engineering, and maths. But with my Azero hat on, I do the same thing, but I do it using a space as a context. So the Azero objectives are to use space as a context to enhance literacy and competencies of young people in STEM, to motivate and enable young people to pursue a career in STEM, and to increase young people's awareness of and the importance of space exploration and space research. And how do we do that? We do that in a number of ways that I'm going to be telling you a little bit more about, but events like this are one of the ways that we promote STEM and promote STEM careers and show the importance of space exploration and space research. We also promote and coordinate the Esa Classroom Projects, and there are 4 of those for second level students. CANSAT is the first one, and it's the most established in Ireland. In CANSAT, senior cycle students are given a kit, an Arduino kit, and they must build a satellite with specifications, and it has to fit in a can the size of a soft drinks can. And then they're launched, and they have to take various measurements using sensors in the satellite. Mooncam challenge students design a habitat on the moon using either Tinkercad or Fusion 360, depending on which level of the competition that they participate in. In AstroPi, students write code, which is run on the International Space Station. And if your code or your project is run on the station, you get a certificate which is time-stamped on the space station. And then climate detectives, in that one, students must identify a climate problem, and then they have to use various data sources to confirm or deny that there's a climate problem and come up with some suggestions for solutions. Information about all these projects can be found on the Azero website, azero.ie, under the projects tab, and then there's a tab for each of the projects. And sorry, I skipped a little bit quick there. As well as honing the technical skills, these projects really help students to develop very valuable 21st century skills that any employer will be looking for, like problem solving, analysis, teamwork, presentation skills, communication skills, all those really important skills that I know you've learned about in the key skills at junior cycle, and also the equivalent at senior cycle in school. The ESA Education Office has an ever-expanding portfolio of classroom resources, and they're all published under the Teach with Space brand. They're color-coded, so the red ones are for primary schools and the blue ones for secondary schools. And the easiest way to find them is just to Google ESA Teach with Space classroom resources, and that'll bring you straight through them, because the ESA website is, if you don't know where you're going, it's a little bit hard to navigate. So if you Google ESA Teach with Space classroom resources, that'll bring you straight to them. And there's just a screen grab of some of the resources that are available. There's quite a few there, all covering very different topics if you just would like to have a look at them. We also support STEM teaching and learning by offering teacher CPD workshops. And you can find details of this on the Azero website, azero.ie, and there under the teacher support section. Upcoming opportunities include our annual Space Education Confluence, which offers an opportunity for teachers to meet with space personnel. Last year, our event was really successful. We got really good feedback from teachers. We used co-creational design principles to design the content and the delivery of the workshop. So we actually went out with a campaign to ask teachers how we could best support teaching and learning of specifically the Earth and Space module at junior cycle. And we will be doing this again this year. So watch out for our Twitter account. So we'll be very shortly, we'll be asking for your feedback. So for now, if you could just save the date for the 8th of October, Saturday, the 8th of October. Last year, we learned what worked very well for us. That was, we focused on one space mission, which was the solar orbiter, and we focused on a specific learning outcome from the Earth and Space strand. And last year it was the benefits and hazards of space exploration. We also have a MOOC, a massive open online course based on climate change. We developed that last year in partnership with our colleagues in Azero UK. It's a free course. It's open at the moment until the 13th of March. There's 3 modules in it. I think it's about 3 hours a week is the commitment, but you do it at your own time. As I said, it's open until the 13th of March, but if you register before the 13th of March, it stays open for a couple of weeks after that. And again, it will reopen again on the 9th of May for 5 weeks for anyone that's interested. ESA themselves offer online training opportunities. There's 3 open, there's 2 open at the moment, and there's a pre-registration then for the summer courses. You'll get that at esa.int/education. So the 2 courses that are open at the moment is ESA Teach with Earth, do it yourself with Earth observation. I don't know what that is, but I think it will be using their EO browser, which is using Earth observation data in the classroom. And then the second one is Code Your Mission to Mars, which is a coding workshop. If you click into those, it tells you the level of expertise that's required. And mostly for these teacher workshops, they're entry level, and people with no experience are welcome and can join. And then the ESA Teach with Space online conference for teachers right across Europe, that takes place from the 5th to the 7th of July. That was hugely popular last year. It was the first time it went online, and it was really popular with teachers who attended. There's pre-registration open for that as well. And again, you get all that at esa.int/education. I couldn't go without reminding you about Space Week, which takes place from the 4th to the 10th of October each year. Again, my colleagues in BCO manage this nationally, and the best way to get information about that is spaceweek.ie. Information about resources, information about events, information about how you can get involved. And I mentioned at the beginning, our next Space Week Careers Roadshow will be the Space Week version, and that's on the 11th of October. So if you enjoyed today, watch out for more information about that event. Also need to mention Science Week, because that's managed nationally by my colleagues in Science Foundation Ireland. Again, scienceweek.ie is the website, and that takes place from the 13th to the 20th of November this year. And then finally, or almost finally, just to ask you if you would like to follow us on Twitter. Our handle is @Azero_IE. That's how we promote most of our events, all of our events and resources. Obviously, everything is on the website, but how we promote them out is through the Twitter platform. So if you'd like to follow us at @Azero_IE, that would be fantastic. And that's my email address if anybody has any queries about anything I've shown you today. Stephanie.O'Neill@sfi.ie. I'd love to hear from any of unfortunately, I can't communicate with the students for child safeguarding and GDPR reasons, but if any of the teachers want to contact me at that email address, I'm happy to take any queries. And finally, I'm going to end with a video about the European Space Agency. And the reason I do this is because there's a couple of reasons. One of the objectives that I mentioned was to promote the importance of space exploration and space research. So I want to share with you the work of ESA. It's a broad video about the many types of work that the European Space Agency does. Second reason I want to share is that everybody knows about NASA, but not so many know about the European Space Agency, or ESA. And Ireland is a paid up member of the European Space Agency. So ESA is our space agency. And I think it's really important that we in Ireland know of the tremendous work that the European Space Agency does on our behalf. So I'll finish with that. I'll play the video and then I'll hand back to Niamh after that.
This is the European Space Agency, dedicated to the peaceful exploration and use of space for the benefit of humankind. Established in 1975, we work together with our 22 member states to push the frontiers of science and technology and promote economic growth in Europe.
Oh, sorry, I don't know what happened there. Hold on a minute, we'll go again.
We have offices in 8 locations across Europe and 1 at Europe's spaceport in French Guiana, where we provide independent access to space for scientific and commercial missions. Exploring space is humankind's greatest adventure and one that we have been involved with for more than 40 years. ESA has the technology and expertise to keep Europe at the heart of the new age of space exploration. From low Earth orbit, we are working to bring humans back to the moon and then onto Mars. By expanding the frontiers of knowledge, we are helping to answer the big questions about the universe. Space provides us with incredible opportunities to experiment and discover, yielding amazing new science. From Earth's neighbors to new worlds, we study stars, galaxies, and look for exoplanets. In addition to astronomy, planetary science, and astrophysics, ESA scientists work on growing food in space, searching for life on Mars, and understanding our own planet. From space, satellites are watching over Earth to monitor its health. Our satellites improve weather forecasts, observe the long-term effects of climate change, and contribute valuable knowledge to Earth science. The Sentinel satellites for the European Copernicus program provide vital information on our environment that can help improve our daily lives. Satellites also help you find where you are and get you where you want to go. We have developed Galileo, Europe's own global satellite system for navigating the globe. With over 20 satellites and a network of ground stations, Galileo provides precise global positioning information. Satellites are also connecting the world, making possible many of the technologies we use every day, like satellite TV and internet access. ESA is at the heart of Europe's satellite communications, developing new telecommunication systems and nurturing European innovation, bringing industry, science, and space technology together. In order to achieve all this, we need pioneering technologies that push the boundaries of the possible. ESA's world-class laboratories turn science into innovation, developing hardware and software for use in space and on the ground. Space technology gets rigorously tested to ensure it can withstand the harsh environment of space and the journey to get there. Traveling to space reliably is at the heart of ESA's vision for space transportation. We launch rockets that carry satellites into orbit and are constantly improving the design of our next generation of launchers, Ariane 6 and Vega C. These rockets and the reusable Space Rider will ensure that Europe continues to have autonomous and affordable access to space. Once in space, mission controllers are operating spacecraft around the clock to watch our planet, study the universe, and explore the solar system. We've flown more than 80 missions, including Rosetta, which landed Philae on Comet 67P, and Huygens, which touched down on Saturn's moon. We operate a worldwide network of ground stations to keep in contact with missions anywhere. ESA is dedicated to making space safer. Our teams help spacecraft to avoid collisions with space debris, and we are developing new techniques to deorbit dead satellites. We bring high-tech telescopes to scan the night sky for asteroids and missions to monitor our sun. With these technologies, early warnings can be delivered about potential asteroid impacts or hazardous solar activity that can affect infrastructure on Earth. ESA's diverse activities are all part of a clear vision for Europe in space. Space is the future, and through ESA, we are all part of it. This is ESA.
Terrific. Terrific stuff. It's such a great video. I always love watching that video, Stephanie. It's just a great review of everything that Esa does. So.
It gives just a broad.
Yeah, it's terrific. Yeah, it's really, really good. So thanks very much for that. I'll let me now guide you through this morning. And Stephanie's given you a really good background there to what Azero does and all the different resources that are available to you after today's Careers Roadshow. But today is really about hearing human stories about how people working in the space sector got to where they are today. And as Stephanie said, we always like to have a theme, and the theme for this particular one for Engineers Week has to be the James Webb Space Telescope, because we've heard so much about it in the news or whatever. So so our two speakers, John and Giovanna, both of those are involved in some shape or form to the James Webb Telescope. So that's what connects us all together. So let me give you context to the James Webb Telescope so that we can all kind of, I mean, you know, some of you probably know this stuff already, so I apologize if it's too simple for you, but you always start at the beginning, I think, whenever we're talking about anything. So this is the beautiful James Webb Telescope. It really is a thing of beauty. It is a collaboration between the European Space Agency and NASA, and also the Canadian Space Agency, which is known as CSA. And this has been something we have all been waiting on for many, many years. People have been talking and working towards creating this telescope since the 1980s. It's a telescope that uses infrared and near infrared light, which I'll talk to in a second what that means, to be able to look much, much, much deeper in our universe. It's enormous. The diameter of the mirrors are 6.5 meters. And the actual mirrors themselves are made up of 18 hexagonal mirrors, and they had to be intricately folded in the launcher. I'll show you that in a second, and to fit in. And then there are these 5 layers of, I guess it's kind of like tin foil or kind of very thin foil that also folded out when the telescope was deployed. And that's a heat shield. And that's really, really important, because you have to be able to protect the telescope from the sun if they're measuring, you know, infrared technology. So the best of the minds of Europe and NASA and people in Canada put this together, and on board there are some really smart science experiments, and Ireland is also involved in that too. So the James Webb Telescope supersedes 2 other space telescopes. One was the Spitzer Space Telescope, which was also an infrared telescope, and that finished around 2020, and that gave us some great looks at some of our exoplanets. These are planets that we discovered that may be like Earth out there. The TRAPPIST one is one of the biggest ones that it would have shown us. And then there's the amazing Hubble Space Telescope, which is still working to this day, but the Hubble Space Telescope is kind of coming to its end of life. And as it's coming to the end of its life, there was a requirement to come up with something different and possibly better. But the Hubble Telescope is slightly different from the James Webb and the Spitzer in that it was using visible light. But we're very excited about what we are going to learn about our universe with the James Webb Telescope, with the technology that's on board, with the fact that it is protected so well with this heat shield, because the Spitzer telescope used liquid helium to keep itself cool, because you have to keep the telescope cool, because otherwise that's the only way it's going to be able to pick up light and heat from the stars. And the way it works this time, it's using its big heat shield to do that. And that heat shield is actually the size of a tennis court. But we want to know a little bit more about the early origins of our universe, and we want to be able to look back into the very first galaxies. And it is believed that we might actually be able to do that with the James Webb Telescope. We may also be able to understand, where do stars come from, where do exoplanets come from, and even some of the moons and planets of our solar system. So maybe we might have a different story about where it all began. Maybe we might get a better idea of a timescale. Maybe we've been wrong in our timescale. This is what's great about science. Science is all about asking the bigger questions. And a lot of the time, our assumptions can be, well, they can be good, but they can be slightly different from where they should be. And we're hoping that we'll get clarity on that from the James Webb Telescope. And these are the instruments on board. You have the NIR spec, you have, I'm just going to minimize this so I can see them, and all of them are using near infrared or infrared. So we have a series of cameras on board, we have a series of spectrographs. So spectrographs will break down light into its constituent colors so that we can monitor and we can measure exactly what we're looking at. And then there are coronagraphs which block out a starlight as well, which allow us look at planets around those particular stars. So they are the main science experiments on board. And I just said already about the Hubble Space Telescope and the Spitzer. So I hope at this stage you may know about the electromagnetic spectrum. So that's about light. So the light that you can see with me right now, hello, as I'm waving at you, that's visible light, and our eyes can see visible light. But there are other forms of light around visible light. Some of them are more powerful and some of them are less powerful. So if you're heating up your sandwich or your pizza later on this evening using a microwave, that's a form of light, and it's a lower energy light to visible light. If you're tuning in onto a radio, that's lower energy light than microwave as well. And then just above microwave is infrared, and the Spitzer Space Telescope was using infrared light. The James Webb Telescope will use infrared light and near infrared light. And then beyond visible light, you've got ultraviolet, X-ray and gamma rays, and that's where some of the light from the sun and stuff can be a bit damaging. So that's how those three telescopes work together. And you can see these are the four instruments, and these are the areas that they're going to be looking at light. So three of them are looking at near infrared, so that's just on the cusp of visible. And then you've got MIRI, which is looking at the mid-infrared. So we will have a wealth of data from that. And like Stephanie said, the James Webb Telescope, after many years of preparation, it arrived in a place called Kourou in French Guiana, and that's it there. You can see the little red arrow, that's the top of South America, and that's a launch center for ESA, and there's been many launches there on our rockets, the Ariane 5 and maybe even the Ariane 6, and this was the launch on the 25th of December. I watched it. I don't know if you guys are watching on a Christmas day, maybe you were opening up Christmas presents, but for all of us space geeks, this was the best present of all, because it had been, it can be anticipated. And I think I showed you there on the very right, because my image is in the way. Look how tightly packed the telescope was in that launcher there. So do you see it was folded up? So the mirrors were kind of folded into three parts. And so when it launched, one of the things it had to do was to open up the mirrors and then also open up the heat shield and turn it into this tennis court shape heat shield. So anyway, as I say, it launched on the 25th of December, and this is footage, let's turn this down, it's a bit loud, of the actual moment of release, which was a big moment for many, many scientists. It's very, very exciting watching it head away to its orbit, which was 1.5 million kilometers away. Now, every moment of an experiment in space, something can go wrong. And so it has been an amazing experience so far. Already, everything that was planned to happen has happened on time. And so the very first beginning of it was this release of the James Webb Telescope into space, and then this unfolding of its solar panels. And it has been consistently keeping up with its timeline. And we've seen some amazing things happen. So the first thing that happened was the heat shield started to unfold, and we got those 5 layers of that kind of tinfoil type thing. And that's really important because we have to face the telescope away from the sun, and to protect it from the sun, we use those heat shields. And I'll just go on because I want to go on here. And this is the timeline of everything that happened. And we're now into, so 25th of December, so we're now coming into month 3, and it is sticking to its timeline. And around about January, it finally arrived at its orbit point. It went to the Lagrange 2 point. And there's these points in orbits between different bodies where the forces kind of equalize between the two heavy bodies, and it means that the ability for an object to stay in that orbit is less than, say, if it weren't in these Lagrange orbits. It would need more energy to stay in the orbit. So the Webb telescope is in this Lagrange 2, which is the other side of Earth between the sun. And as I say, the tennis court part of the telescope is facing the sun, and we have our telescope looking out into the universe. And so it's still testing, and it will be for 6 months, but we have watched some really interesting things being reported. So you see the shape there on the left. So that's all the different mirrors focusing on the same constellation. And so I think this is a GIF. If I play it, maybe it'll work. Yeah, sorry guys. Duh. If I play the GIF, you'll see that it changes. So it goes from kind of blurry to very focused. And then we had our very first selfie then in earlier that month in February. So we continue to wait, and in 6 months time, or at the end of 6 months, we're going to start getting data. And as ESA members, as Stephanie said, we will have access to that data. So it's very exciting, and it'll open up a whole new channel of understanding of our place in space. So we thought that would be useful for you to know about before we went into hearing from our speakers. And I'm just going to get rid of that. And so let's get going, shall we? I mean, I've talked enough, and it's time to hear other people speak about far more interesting things. So I'm going to bring in somebody I've already been speaking to. If you watch the promotional video, I interviewed John, and actually his interview is up on the Space Careers portal on the Azero website. And John Ward, you're very welcome to join us this morning. And John works at Railtra. How are you? It looks like you're in a very sunny spot. Where are you, John?
Yeah. For once, we actually get some sunshine here, so I have the blinds down. But thanks for having me, Niamh.
Very nice. No, it's great. And you are a systems engineer, but tell us about your career. And I'm sure you're going to mention James Webb at some stage in it, but tell us about how you got to have such an exciting job that you did.
Well, do you want me to start the presentation, or do I just give it?
No, whatever way you want to do it.
I think I'll tell the story probably a little bit through my presentation here, and I will share that now. So let me know if you can see that okay?
I can see that fine. Yeah.
Yeah, super. So as Niamh actually mentioned there, showed this beautiful video of the James Webb Space Telescope as it's drifting away from the top of the Ariane 5. And that video that video came from a system that was conceived of and built in and tested in Ireland by Railtra, by the company I work for. So my name's Johnny Ward, and I started my career as an astrophysicist in academia for several years before I transitioned into engineering. And I'll kind of give you that whole meandering path of my career. But before I started, the first thing I wanted to say is that for all the students watching, that this is just my story in STEM. And so I'm from Donegal. I'm from a different generation to everyone watching this, because none of you were born probably when I was starting secondary school. But so what that means is I have my own unique upbringing, and so I had different challenges and different advantages, and good luck and bad luck relative to you. So, what I'm going to tell you is not the correct way to have a STEM career. It's just one way. And so you'll all figure out your own ways about how you want to enter into this world. And the other thing as well is be a little bit wary if you're comparing yourself to me. For example, I have years and years more experience than anyone, and I'm only showing you all these beautiful pictures and successful moments, but there was plenty of bad moments as well, which I might dip into. And then one little bit of advice I often found, and this helped me a lot throughout my career, was I had to stop sometimes and ask myself some very deep questions, but they were essentially, what did I specifically like about what I was doing? And what I mean by that is, if I'm working with my hands in a lab, what is it? Is it exactly that I enjoy doing? And do I need to be in the job I'm doing, or do I need to be in academia to do that job? For example, could I an engineering context in a startup? And so those are questions that I had to ask myself throughout my career. And it's something I think it's important to ask while you're making these decisions. One little bit is just beware your ego when it comes to making STEM choices. So some things you can find is you have to be very careful about your motivations for why you're picking stuff. And if you're saying you want to be a physicist because people will think I'm smart, that's not a great long-term motivation, because when you're in a difficult situation, when the pressure's on, or when you're struggling to solve a problem, that's not the thing that's going to make you work harder, just because you're relying on other people's input for your own self-esteem and for your own self-fulfillment. So that's something I'm going to try and maybe bring into here. I have another slide which kind of just maps out essentially my career to date, which is, perhaps not typical, but it is typical in the academic context, because academia is a bit of a nomadic lifestyle. You have to move from university to university while you try and find a permanent job, and then industry can be a little bit more stable. But from the very early days, I was interested in kind of the night sky, and that's, I really think, because of my environment. So I grew up in Glanties in County Donegal, which is actually I think designated a dark sky area, meaning very little light pollution. So for me, growing up, I was exposed to a pretty phenomenal night sky when it wasn't raining in Donegal, so that was pretty rare. But my father would bring me out with a small telescope, and we would go stargazing. So I think from a young age, that already started to instill a kind of an interest in the universe and astrophysics as such. But when I was in secondary school, I did many subjects, and we could talk about that later. But one thing I did focus on a little bit was taking honors physics and honors mathematics. But I did other subjects, of course, and I think something we can talk about is that it's important as well to stimulate your brain, because imagination is a crucial part of being a scientist or an engineer. You have to have the ability to think outside the box, and so things like music and art, I think, are critical to that. Ultimately, then, when I was in secondary school and thinking about, okay, I'm kind of good at physics, or at least I enjoy it. Is there something I can do here to give me a career out of this? And so I did a Bachelor of Science in Maynooth, which is in physics with astrophysics. Now, even at that stage, I was thinking, well, okay, physics is a useful degree, because at the very least, it'll give me options to move into various industries. So if things go wrong, or if I realize maybe a career in physics isn't for me, well, at the very least, because of the training you learn as a physicist, as a problem solver, it could be something that could be very useful in many fields. And I have many friends who've done this degree, and they work as managers in Aldi, or they work for Google. But all of those roles involve problem solving, and I think being a physicist helps you train for that. Throughout this as well, there's moments that I think are really important, and some of them were getting internships at Chicago, for example. I'll speak a little bit about that. But a lot of those things help differentiate your CV. So everyone is a lot of people are doing third level degrees, and that's fine. It's a good basis for everything. But sometimes you need that little special sauce, and that could be done through an internship or some projects that you do. And so a lot of my career was informed by taking a risk and emailing people and trying to find out, do you need someone that can do this, or can I work here, just to start adding on to my CV a little bit and differentiate me. But you can see throughout my career, I had to move to the United States. I worked at NASA Goddard for 6 months as part of an experiment there. Then I moved to Spain, in Bellaterra, which is outside of Barcelona, but I worked at an institute there, and that involved telescopes in La Palma. And then I moved into industry. So at a certain moment, I went, I don't know if academia is going to work for me. I don't know if I'm going to get the permanent job that I need. So I'm going to take all the skills I have from academia and see, can I transition into something that I still find enjoyable, which is space-related work, but it's actually in the engineering side. And so I went into a startup company there in Barcelona, and then kind of after 8.5 years away from Ireland, wanted to come home. And luckily, Realtor Space Systems Engineering was just starting. And I sent an email through their website to see were they looking for somebody, and I got a response. And a week later, I had an interview in Dublin, and a month later, I had moved. So the thing here is that just to show that this is all kind of it was never all smooth, and there was a lot of little fluctuations in terms of my career. But ultimately, this last slide, the last logo won't be my last, and maybe that I'll change job again. You can already see I'm a space product manager now, and maybe in the future it'll be a completely different thing. But the one thing I wanted to show is that there's 25 years here. I started secondary school in 1997, which terrified me when I wrote this out. But there's a lot here, and so I'm going to have to blast through my slides because I have a lot to say. But one of these things when I talked about was this University of Chicago internship. So these were moments that gave me some really great experience early on. And what actually informed a lot of my research was cosmic ray physics. Now, a cosmic ray, it's a particle that comes from outer space. There's a rain of these that hit our Earth constantly with huge energies. They travel near the light, a lot of them, parts of elements, And what's an element? Iron, a strontium particle, a gold particle, silicon. All of these atoms are raining down on us. And for a long time, we had no idea really where they were coming from or how they got this energy. So how do you measure these, or how do you study them? Well, you build a detector, you put it on a giant balloon here, which is the stratospheric balloon, they call it, which brings your detector to 40 kilometers above the Earth. And that means that the atmosphere is no longer blocking these particles. The atmosphere acts like a meter of lead in terms of blocking radiation. So if you want to measure these particles, you have to get above that. But early on, what that gave me was this great experience as an undergraduate. I got to work with real experiments. I got to order parts, put them together, and work in very high pressure situations, such as when this is launching, monitoring the payload and stuff. And then this was me when I was much younger with more hair. And you'll see a lot of photos of me with Donegal jerseys, so apologies for that if that triggers anybody. But this was a launch from S-Range in Kiruna in the Swedish Arctic, so really incredible experience at a young age. Then I moved on into gamma ray astronomy. So Niamh had shown you the electromagnetic spectrum, and in the corner at the very, very highest energies are gamma rays. So these are the radiation that turned the Hulk or Bruce Banner into the Hulk as such. But this allowed me to again keep working on cosmic ray origins, because weirdly, when these particles smack into each other with such high energy, they actually generate gamma rays. So when you're searching the universe for gamma radiation, it's like looking for the smoke of a fire. And so this brought me to Arizona for several months, and also to La Palma, where I worked on the MAGIC experiment, and Veritas was the experiment in Arizona, which Dublin and Ireland was actually one of the pioneering countries involved in this entire field. But for students, okay, that's very cool. However, what do you actually learn from all this work? Ultimately, with gamma ray astronomy, what you end up doing is you analyze data. So what that means is you collect these gamma rays, but you have to write programs to clean the data and make these beautiful little sky maps here. So what in the bottom left you have here is the Milky Way, our galaxy, with gamma ray eyes. So this shows you lots of little exploding stars, which we believe cause these cosmic rays to exist. And then when they hit into each other, you get this gamma ray glow. And this is actually the top right here. Is the black hole in the center of our galaxy. Now, yes, you can't see a black hole, but all the material spinning around it and falling into it actually generates gamma radiation. And so these are maps of that. But what this work helped me learn was, programming languages, presentation skills. So when you're presenting your results to the scientific community, documentation writing, so writing scientific papers, clear, concise language, getting your message across. Teamwork, these are big experiments, hundreds of people, technicians, engineers, and scientists. You all have to work together to make sure that this system works so that you can make these beautiful images. Furthermore, then in the stratospheric ballooning thing, so this was really the core of my academic career. I would say I worked on something called the Super Tiger experiment, which was again about detecting cosmic radiation, cosmic rays, and trying to understand where they were coming from. And this is where I really started to get the engineering bug, because you can see here we were making these types of detectors which would allow us to know when a particle entered and exited our entire detector stack, which you can see examples of here. A lot of electronics work and debugging that. Then environmental testing. So you can see on the right-hand side, this is a huge chamber which they suck all the air out of to, nearly all the air out of, to simulate the environment that our balloon experiment. When you're above 40 kilometers, you're above 99.9% of the atmosphere. So it's nearly space. But we want to see, does our experiment work when you remove all the air out of the system? And so this was already this environmental testing I'll talk a little bit about, because it's extremely important in the context of space engineering. You have to test your system to make sure it'll work in space, because you can't get up to fix it. And again, the other, always data analysis and programming, and a lot of teamwork. So again, you see this is only partially the team. But really then we had to launch this thing, and we went to Antarctica. Now, why Antarctica? You go to Antarctica because in the summer months in Antarctica, the wind pattern sets up in a cycle. And when you put your experiment on a big balloon, it means it goes around in circles. And if it falls off the balloon, it's not going to fall on anybody's head. And so we ended up flying, because I was with the United States University, Washington University. We flew down with the US Air Force. And we built our experiment up again down there. And again, this is the team, the Super Tiger team. So it wasn't just me, I was part of a team, and we all had to support each other and make sure that we got what we needed done. Here's the bottom right, the balloon inflating, and in the right there is Mount Erebus, which is actually the most southerly active volcano in the world. So always kind of looking nervously over at it while it was smoking. Here I'm just going to quickly show you, because I'm mindful of time, that we launched. This is an example of launching a stratospheric balloon. So you can see it releases. I don't know if you saw the Super Tiger experiment with us standing in front of it, how big it was. So this just gives you a sense. That's it down in the bottom left on that little crane. So this just gives you a sense of how big these balloons are. So that's the Super Tiger experiment there. And then what happens is, at a certain moment, they decide that the wind has caught the balloon and you're going to let it go. And once that balloon gets up to the upper atmosphere, it inflates so much that you could actually fit Crow Park inside of that balloon. So that just gives you a sense of how ginormous those are. Now, that's all cool, lots of nice photos. But what do you do when you launch your balloon? Well, you have to monitor the experiment, make sure that it's working. I was down there for 96 days in total, but 55 of those days was simply looking at the performance of the experiment to make sure that we monitored all the housekeeping, which means all the vital. Sure it was working. And it's 3 orbits around Antarctica of the balloon, so they're just different colors. And in the end, you could see it landed up there. I grew a very big beard. You go and look.
I think we've lost him. Have we? Is it me or has?
I also cannot hear him anymore. I was wondering if it was my internet.
I thought it was mine as well.
Yeah.
So not to worry. I mean, John's talk is fascinating. I mean, he's had an incredible career at the Antarctica. I was so jealous when I was interviewing for the video. If we've lost John, you can watch you can watch him talk on the video that we have. Stephanie's actually just put it in the chat there. So you have it there on the Azero Space Careers portal. He's had a fantastic, really fascinating career, and he's moved into industry, and I'm sure he was going to tell us that. And there's some really great nuggets there in what he was sharing. I think he's coming back in. Let's see if we've time for him to tell us the rest of it. We are running a little short on time, but hopefully. Hi, John, you're grand. Hey. Don't worry. I was just talking. So you're grand. So if you want to finish if you just want to finish up, we'd love to hear the end of your presentation. It's fascinating what you've been doing already. So I'm going to stop talking. Take over there.
Okay, sorry. So can everyone hear me okay still?
Yeah, we can hear you. Just froze for a second. That's
okay,
all.
Okay. So one thing I'm going to just briefly talk about is that in Realtra, you're making these video kits. And one example of what I show you is that you need to build your electronics very carefully, but you have to test them. And so one of the jobs I do now is we drop a giant hammer onto pieces of metal, which simulates a shock on the rocket. And you can see this is one of the cameras we referred to in the JWST here. So this is the type of work I do now.
You just need to share, if you share your screen again, John.
Sorry, excuse me.
No problem, no problem at all.
Of course. It's disabled. Can someone let me share?
Oh no. Yeah, Robert, Danielle, can you give John sharing privileges again? There you go. Off you go. You're the co-host. Go.
Okay. Yeah, sorry. So one of the things, again, we do with testing the video kit for Vicky, for example, and this is the example of the video system here. It's one of the cameras, but we have to make sure it can survive the environment of space. So one of the tests I end up doing here is that we drop a giant hammer on the, let me do it again, drop a giant hammer next to our camera, which you can see here on the left. And that then simulates the shock that happens when the cone of the rocket blows off. And so this is the type of work we end up doing there. So document thing that unfortunately you're going to have to deal with. So lots of work about making sure that your experiment does what it's supposed to, that it can survive the environment of space and arrives on time within budget. So a lot of reading of documents. And this is always the meme I like because this is what I actually do. cool photos, but there's a lot of Word and Excel documents. So the only core point, just to summarize here, is email, phone, make connections. You have nothing to lose by reaching out to people. No one's going to give out to you. Be shameless, because that way you'll end up putting yourselves in positions to get jobs and to get internships. Helps with your CV. And then other things you can do in STEM. There's health, law, art, business, journalism. It's an industry, so you need all the pieces to work in this industry. And in the Irish space industry specifically, we're growing at a big rate, but we need engineers and physicists and entrepreneurs and all this type of stuff. So please consider this career, and it's a lot of fun, and it's important now because Ireland is the space industry is growing, and we need you.
Yeah.
So thanks for your attention. Sorry that took a long time, and here's my Twitter handles, etc. So feel free to reach out.
Just leave them up for a second as we're finishing up, so that people can see them. That's terrific. I'm so jealous that you got to work in Antarctica and the Arctic as well. So you've had a really varied career, and you've summarized it really well, and it is a personal journey and a personal quest, but I think you're a perfect example of somebody who just thought outside the box and reached out and thought about internships, and that's what's gotten you where you are today. So thank you for sharing. But we'll go into more detail when we get into the breakout room. So don't forget, you can ask John any questions you want. There's actually a prize for best question coming up shortly when we after we hear from Giovanna. So John, thank you so much. If you unshare your screen there, I might bring Giovanna forward. Stephanie, have you anything that you want to say, or you just
I just wanted to reiterate, because I thought it was really interesting. A quote from John was, imagination is a crucial part of being a scientist or an engineer, problem solving and thinking outside the box. And I think if people take that message home today and nothing else, I think that is a really powerful message to take away from today.
Thanks, Sean. Yeah, because sometimes it's hard for people to understand what an engineer does, but I think you've captured it really, really well. So thanks, John. So Giovanna, how are you? And you're in Leiden, and that's a city in the Netherlands near the Research and Technology Centre in Noordwijk. That's correct, isn't it?
That's correct. Yes.
What's the weather like in Leiden?
Well, it's wonderful today. So unusual. It's No, we are having a good streak.
Good.
And I'm happy to be with you.
Lovely,
only virtually, but very nice opportunity.
Yeah, we'd love to hear from you. So please, in your own time, take it away. I think you should have sharing privileges, and we're really looking forward to hearing about your carear and how you got to.
Yes. So as you said, I'm an instrument scientist. So I'm trained as an astrophysicist, and I work as an instrument scientist for ESA. And the so what is an instrument scientist? An instrument scientist is it's a scientist that look after the development and the calibration of an instrument for other scientists to use. And the instrument that I take care of is an NIRSpec. So I'm going to share my PowerPoint here. So I have to put the play from start. So can you see the slide where you can see NIRSpec?
Yes, I can see it.
Yes, so this is the near-infrared spectrograph built by Europe, and it's one of the scientific instruments on board of the Webb telescope. Like you said, Nive, is a spectrograph, so we use it to decompose the light and look for signature of elements in the spectra of lights. From that we can understand what are the physical condition of the object that we are looking at in terms of composition, temperature, pressure, density, and so on. So it's very important if you want to understand the physics that's going on in that particular galaxy or in the atmosphere of the planet, and so on. So this is the role of NIRSpec. This is mounted here at the back of the Webb Space Telescope. I don't know whether you can see my pointer.
Yes, we can.
Yes. So like the other instruments here, receives the light from the primary, is reflected on the secondary, and then focused here over the scientific instruments. And so NIRSpec will play a very important role in addressing the scientific questions that are the goals of the Webb telescope. And they are summarized in these 4-part slides. So from investigating what we call the first light, so the birth of galaxies, at the few 100 million years after the Big Bang, what we consider the beginning of our universe in our current model, and then study the evolution of the galaxies from this initial shapeless spheroidal form that we see, how they grow into the beautiful grand spiral structure that we see in our universe. In fact, we live in one of them, the Milky Way. And then zooming into our galaxy, study the birth of stars. And like you said, with the infrared light, we can really peer to the dust envelope that surround the young stars and understand better the mechanism that are playing in the very first stage of a star life. And finally, study the exoplanets, so what we call the planets orbiting other stars, as well as planets in our solar system. But in particular with NIRSPEC, we will be looking at characterizing the atmosphere of the exoplanet. So indeed looking at the composition of these other worlds, of these alien worlds, whether they have oxygen, water. Obviously, these are very exciting questions, as you can imagine. So I don't do the work as a project scientist, as an instrument scientist alone. I'm part of a large team. This is the JWST ESA science operation team. So I wanted to share with you these slides just to show again and to emphasize, like John did, how important is teamwork. These instruments, these experiments are extremely complex. So you need very different set of skills to do a proper job, and you can see there, and we have that in our team with members from all over Europe. And one of the role of our team was when the Webb was on the ground, was being prepared. We looked after the ground testing of the instruments. Here you see a picture of the Webb telescope, so the primary mirror, the instruments are at the back, like I said, and it's going to be placed in this huge cryogenic chamber. So this is a chamber where you create a vacuum and where you reproduce the temperature that the instrument will be operating in space. So we're talking minus 230 degrees Celsius, extremely cold. And then we were in charge of taking the data from our instruments and understanding that things work as they should. So we are not the people in this white overalls. So these are mainly engineers and technicians. We sat behind terminals. And I want to point out these funny pictures. So this was indeed during this testing at Johnson, so where you saw the big chamber, and we were hit by a huge hurricane Harvey, and we had 10 days of pouring rain. And as you can see, we had to shelter our equipment under a plastic sheet. So not a very high technology moment, but we managed. And this is another cryogenic chamber from Goddard. This is from a test we made earlier on of our instruments. So those were only the instrument alone, again, placed in this chamber that reproduced the condition of space, so that we could analyze the data and make sure that everything was performing as expected. As I said, we work as a team, so we have meetings in which we discuss plans and issues that need attention. One of our role is to train the astronomical community in Europe. So here you can see people working with their laptops. So this was doing an event in which we presented our instrument and the tool that the scientists need to be able to use in order to perform the science with this complex instrument. And it was a 3 days training. And then finally on the right, this is a much more recent picture. This is a colleague, and he's finally looking at data coming from space. So NIRSPEC is up there and transmitting telemetry. And so we are looking at the data, and we are starting to perform the activity that will make near-spec ready for the science. And that's the goal by the beginning of this summer, to have the first science observations, so to point the Webb telescope to look at stars, planets, globular cluster, galaxies, and see this under the new light and with the powerful instrumentation of the Webb. So that will be a very exciting moment, and it's a moment that we are really looking for, but we are working hard to achieve. There is a lot of things that need to happen from now to June before the instruments are ready for these observations. So I also try to capture here, just to counterbalance what it looks like, also quite a bit of a glamorous side of our job, which is certainly there, and it's certainly very interesting, but there is also a lot of everyday work with many hours at the computers. So one of the things that takes a lot of our time is email. We write a lot of email, we read email. Communication between scientists and engineers is it's really crucial. We code. We write software. These data and these instruments are nothing like existed before, so we have to write our own solution and our own processing. And then we write technical notes to document what we do, what our proposals are, and occasionally we also write a scientific paper, either on our on instrumental aspects or also on science. Some of us are involved in the study of the physics of primordial galaxies or the atmosphere of exoplanets. So if I had to summarize in a few bullet points the work of an instrument scientist, an applied physicist, I think I'm going to just repeat very much what John says. There is a lot of data analysis, and this involves coding and using mathematical methods. As more applied physicists as we are, we have to think about the tests that we have to do with our instruments, the activities that are coming. So there is planning, solving problems. There are always issues, things that we don't expect, things that are more complicated to achieve that we had planned. Yeah, that's very much the fundamental activity skill. And then we have to document our findings, solution, communicate with other scientists and engineers. Occasionally we attend conferences where we present our results, and occasionally also we have outreaching activity in which we try to communicate our work and the excitement of the science that can be done with our instruments to the general public. So how did I get to do my work at the European Space Agency? So I come from a small town in the north of Italy. I gained a diploma from the high school, a state high school. None of my family had been to university before, so it wasn't an easy solution for me after my diploma. I was in a way interested in many things. I was interested in literature, philosophy, math, chemistry. was kind of difficult. But at the end, I focused between. I was undecided between philosophy and physics, because fundamentally I was very interested in nature, understanding how nature works. I also come from an area with the dark sky, and I was also very fascinated by the night sky. And I thought that the approach of physics to understand our world is more practical. It's more like looking at nature and learning from nature, as opposed to the philosophical approach that is more maybe reading what other people think, processing that, and it is more intellectual, abstract work. Both interested, but for me at that moment, it felt that physics was something more close to my interest. So I did a bachelor laurea in physics, and I did like what the studies involved. I didn't mind there is a lot of math, but I didn't mind it. I took it very much as a game, math. At the end, it's a bit it's a challenge, and you have to solve problem. Again, it's less studying and more challenge and more working out the solution in your own head. And then I like that. So I took a master in radio astronomy at University of Manchester. You can see here the beautiful picture of the radio telescope in Jodrell Bank near Manchester, and then a PhD of astronomy at University of Milano. And then for personal reasons, I went to work for a software company for 1.5 years in England. But as I said, you learn a lot of coding as a student, a PhD student in this field. So it's not difficult to find this type of job. And I think this is very true also nowadays, especially with the explosion of data science. But at the end, I decided that was not really my world, and I really was more fascinated by fundamental question of the universe. So I applied for research fellowship at ESA, where I stayed for 2 years, and then I remain at ESA at the Esa Centre that you see here on the right in the Netherlands. And I've been there since 2001. Again, when you look at this number, gosh. So a long time has passed, but as I said, it's been a very interesting walk of life. And I just want to finish with this slightly very light philosophical, as you say. I'm interested in philosophy, and stress that as well as the destinations, just as important thing is the path that we go through life. And so there are many paths to space science. There's the obvious STEM path, which I took, and I'm very, very happy. But as John said, there are also commercial aspects, law aspects, communication aspects in space science. So I think it's important to enjoy the path, look out for new vista, look out for opportunity. Like Stephanie pointed out, many opportunity to approach things, try things out. So that's
great, Ivana. Thank you so much. So interesting. It's so interesting, and we're getting lots of questions, people coming in. And again, don't forget there is a prize for best question. We'll be shortly leaving our YouTube community, and the groups here joining us on the Zoom call will go into breakout rooms, and you'll be able to find out more directly from Giovanna and John. Such a fascinating career, and I think it's so exciting to know what James Webb is going to give us as well. It's just
it's going to be.
We're all looking forward. Yeah, we're all looking forward to it. So we have a question about just space careers in Ireland, and I don't know, maybe Stephanie, you might be able to answer this one, but Deborah Malone asks, is there any resource for finding space-related careers in Ireland? Or maybe Giovanni, you might know it too, working at ESA. I don't know, or John, would you know? The question is there any resource for finding space-related careers in Ireland? Well, I mean, the Azero.ie Space Careers portal is one. Is there anything else we could think of?
So one, maybe it's a little bit rowdy, but how I did it myself was Enterprise Ireland has a website with lists all the companies in Ireland that are involved in space, and what I did was go through them and send an email to a handful of them. There's Space Careers maybe.com, I believe, but that may not have a lot of Irish specifically ones, so it may have to be a little bit more organic and direct reach out to people.
All right, thanks.
Sorry, I was on mute there, Niamh. Just to say, we promote profiles of space careers, but we don't advertise for jobs in the space sector. But like Johnny was saying there, Enterprise Ireland do have a department that work with the space, specifically with the space sector, so that would be a good starting point. Also, there is an industry group, the Irish Space Industry Group, ISIG. I think they have a website, so that might be another port of call. Do you know, John, do they have a website, ISIG.ie?
Yeah, they do, absolutely. And you'll find, I'll put the website in.
Thanks, Johnny. That's
because
great.
the co-founder of my company is one of the
Brilliant.
5 years of ISIC. So I'll put that in.
Giovanna from YouTube, we have a question for you. Is there a reason we want to see the atmosphere of planets? Why do we need to see the atmosphere of planets?
Yes, so we, in the last 20 years, we discovered a lot of planets around the stars in our solar neighborhood, so other stars than the sun. And it's a big effort undergoing to try and understand what these planets are like in terms of size, in terms of density. And now with the Webb telescope and the NIRSPEC and one of the spectrographers, the opportunity opens to actually probe the atmospheres of the exoplanets. We have done that to a certain degree with Hubble already, so this is a tried technique, but the sensitivity is at the limit. So there is still a lot of uncertainty in these measurements, and we can only target really kind of big planets with large atmospheric, a bit like Jupiter type of objects. Webb is more sensitive, and it operates in the infrared, in the near infrared, which is a better wavelength for this particular study. So the idea is really to understand what elements are present. Ultimately, of course, the very exciting goal is to understand whether there are planets in what we call the habitable zone. So in the area where the temperature are reasonable for our model of where life could possibly exist, and understand whether the atmosphere of these planets have elements like water or oxygen. As you can imagine, that would give us a very new view of our environment, and possibly say, okay, on this planet, in principle, life is possible. So so that's the very excitement, but this is just the very exciting question. Of course, in general, by studying the atmosphere of exoplanets, we improve our models of climatology and atmosphere circulation. So actually this has also impacts on our model of climate on Earth, because with more data point, you can improve your models and so a better understanding of atmosphere circulation, climatology, and so on.
Yeah, so lots of reasons to study.
Lots of reasons, yes.
Lots of reasons. I'm watching the clock, but we do want to kind of give air to the questions coming in from YouTube. But I'm going to just ask this question to you, Johnny, and it's, we're using Raspberry Pis and microbits to explore space concepts. These are fairly new, so we're wondering what tech or code got you into software and hardware for space. So nowadays you have Raspberry, I think the question is, nowadays there's Raspberry Pis and there's Arduinos, but what got you into it in your day?
So funny, in my day, when I was in university, we started with C. I did a little bit of Java, but ultimately the main language that I used was C++. So I think actually that's still relatively common. Yeah, but I would say that what we find now that's very useful is Python. And I think that's one that's very useful from a data analytics and things like that. I'd recommend it.
Brilliant. Okay, I think, Stephanie, we should probably stop and go into the breakout room. So we're going to say goodbye to our YouTube participants. Thank you so much. Thank you so much for your questions. As you can see, it's a really interesting discussion that we're having here, and two super examples of really interesting careers in space for our Engineers Week. So goodbye, YouTubers, and don't forget, come back again. We've got another Space Careers Roadshow coming up during Space Week, which Stephanie told you about, and Science Week. So goodbye, and we'll now just continue with our Zoomers that are joining us. So the next phase of this is you're going to get a chance to talk in more detail with both John and Giovanna, and we're going to split you into two groups, and you'll have a few minutes with both, and we'll swap you over. Don't forget, there is a prize for best question in both groups. Yeah.
Sorry, Niamh, there's a bit of a change of plan.